Welcome to our presentation on our compiler design project. We used the commercial software Antler to generate some components of our compiler, and we implemented the rest ourselves. Following is a description of some of our design choices, difficulties we faced, teamwork and development methods, and work to be done in the future. So Antler provides two different approaches to traversing the parse tree, the listener class and the visitor class. Our group used the visitor approach. We implemented the visitor pattern by extending the base visitor class that is generated by Antler and overriding the visit methods for certain parse rules. We used our visitor implementation to populate the symbol table and generate the abstract syntax trees. The reason we used a visitor pattern instead of implementing our own code was to reduce development time and because it provides a standard way of traversing the parse tree. The figure shows the call sequence for the given parse tree using the visitor pattern. Choosing to use the visitor pattern over the listener pattern was one of many design decisions our group had to make. By using the visitor pattern instead of the listener pattern, we were able to return data at each node instead of having to store the data in variables, reducing the memory usage of our program. However, because some nodes needed to return multiple types of data, we had to use tuples, increasing the complexity of our program. The two figures show the differences between the visitor and listener pattern. Since we used Python 3 as our programming language, we ran into several issues with our grading script. Our main difficulty was installing the Python runtime package for Antler. We didn't have sudo access on the ESUS machines, so we could not install the package to the global package location. Instead, we had to use the Python virtual environment package to create a virtual environment and install the package there. We then had to run Python from within our virtual environment. The figure shows the code we used to do so. Because of the project reduction, our compiler was not even complete. Continuing forward, we would implement code generation for the rest of the language, which includes the control structures and function blocks. We also need to implement error reporting to report to the programmer where syntax errors or invalid tokens are located in the source code. And lastly, our group did not implement any sort of code optimizations, so we would try to implement some like common sub-expression elimination, p-poll optimization, register allocation, and instruction scheduling. Team member 1 did a majority of the programming and design, along with writing some of the technical report and doing the presentation video. Team members 2 and 3 helped with some of the programming and did a majority of the technical report and portfolio. All members contributed roughly the same amount of time to the project. Lastly, our group used the iterative software development lifecycle model. We designed solutions for a single component and implemented them. We then evaluated the implementation and moved on to the next component. Each step built off of the previous step, allowing us to progressively build up a working compiler by developing the components iteratively. This helped our team because we were able to learn the material as we went instead of having to know about all the components from the beginning.